Hey guys, welcome to a new lesson. It's a little bit of a long one, so we're gonna do this over 2 days. Um, we'll start off with some review board questions and pause the video as usual and give them a go and see if you can figure them out. So the winch in the above diagram is used to hoist up a mass 15.2 meters. What is the magnitude of the mass if it gains that much gravitational potential energy? So we're going to use, actually I'll just switch cameras here. Be a little bit easier. So you have EP equals mgh, and we are trying to find out what is the magnitude of the mass, like that. So our gravitational potential energy is 3.25 times 10 to the 4. G is 9.81 meters per second squared. And then our height is 15.2 meters. So typing that all in, 25 times 10 to the 4 divided by 9.81 times 15.2. And we get 217 kilograms. So our answer is, didn't round properly, 218 kilograms. So our answer is A. An artillery shell with a mass of 12.5 kilograms is fired at a speed of 564 kilometers an hour. Find the shell's kinetic energy. Okay, so I'll do this one as well. So we'll use our kinetic energy formula. EK equals 1/2 mv squared. So 1/2 times the mass of our artillery shell, 12.5 kilograms. And it's going at a speed of 564 kilometers an hour. So when using this formula, if you got the wrong answer for this, you can't be in kilometers an hour. So we have to switch that 564 kilometers per hour into meters per second. Okay, so there's 3,600 seconds in 1 hour, and then kilometers into meters. And there are 1,000 meters in 1 kilometer. So we would go 564 times 1,000 divided by 3,600, and we get 156.6 repeated meters per second squared. So you always have to be, it's not squared, it's just that, and then this is squared. So you always have to be in meters per second. So I'll square that answer, and then I'll multiply it by 12.5, and then I'll multiply it by 1/2. And we get 1.53 times 10 to the 5 joules of kinetic energy. So C looks like it is the correct answer. Okay, and then number 3, a tow truck is traveling at a constant velocity on a city street. The driver sees an identical tow truck broken down. The tow truck driver tows the identical tow truck, but is driving on the highway, which is double the speed. So it looks like we are doubling our mass and we are doubling our speed. So what would be the change in kinetic energy for the tow truck? Okay, so it wants to know about kinetic energy. So remember, when doing these, leave some spaces in between and try to use a different color for your changes. So we are doubling the mass, and we are doubling the speed. So because velocity is squared, we have to square this number. Mass isn't squared, we don't have to worry about that. So the changes we are making are 2 times 2 squared, which is 8 times. We're changing nothing on the bottom. So my kinetic energy is going to change by 8 times as well. So C, 8 times is the correct answer. Okay, and then what are the base units for a Newton? Let's give that a go. So to find the base units for a Newton, you write out the formula. Okay. Mass is in kilograms, acceleration is meters per second squared, force is in newtons. So a newton is equal to a kilogram meter per second squared. So C is the correct answer for that one. So we get C. Okay. So this is our new lesson, work and power. Like I said, it's a little bit of a longer one, and it's got a ton of homework for it because there's a lot of stuff packed into this lesson, and a lot of this stuff we've done before, so we don't need to take a long time doing it, but there is lots of questions based on it. So that's why I'm doing this over 2 days, just to give you a chance to do that homework and make sure it's not too overwhelming. Okay, so your definition for work is a net force applied over a distance. So if I pushed on a desk and I moved it 3 meters, I might be doing work. Okay, we'll talk about why you might be doing work. So if you don't move any distance, you don't move any work. So if you push on a wall and you're not moving, you're not actually doing any work, right? So what the goal of work is to give or take away energy. If you change the energy of something, then you are doing work. So if we go back to this example here, if we move a desk 3 meters, well, if I take that desk and I push on it, that's my stick man, so I'm pushing on it, and I move at a distance of 3 meters, well, I could be doing work, but I could also not be doing work, because if I move it at a constant speed, well, I'm not technically doing any work because I'm not giving it any energy or taking it away. I'm not changing the energy at all. And that's because if we look at that desk that I'm moving, well, if it's moving at a constant speed, I have a force applied moving this way, so I'm applying a force. But there's also an equal and opposite force of friction to make it move at that constant speed. So because I'm applying a force this way, but friction is canceling out that way, we don't have any net work done, right? Just like net force, there's no net work being done. So, but if I push on it and I accelerate it over 3 meters, then it's speeding up, then yeah, I'm definitely doing work. Okay, so if you change the energy, you did work. And that's how you should think about work, is did I change the energy? Okay, then I must have done work. So the 2 types of energy that we're going to focus on changing in Physics 20 are gravitational potential energy, so that MGH, right? So lifting a rock a distance of 1 meter, yeah, that's definitely doing work. Whether you do it at a constant speed or not, if you lift it up, you're giving it gravitational potential energy. Okay, and then this one is better written, right? Pushing on a car to speed it up. Yes, if I'm speeding it up, then I am giving it kinetic energy. I am doing work. So these are our 2 formulas for work. So work equals our change in energy. Right, and this could be any type of energy, kinetic, potential. It could even be like chemical, but we don't really focus on that in Physics 20. And then this is also another formula, our net work equals our net force times our distance, right? So in Science 10, you talked about force times distance, but we want to talk about net work being done so that we're actually giving it energy and we're consistent with that. Okay, so work with a constant or average force, force is in newtons, distance is in meters, delta E is our change in energy. Like I said, it could be any type of energy. So to find these formulas, you can find them on your formula sheet here. So we have work equals force times distance right here, and then we have work equals change in energy. So they're the first 2 on the left side of your data book. So with using work equals change in energy, this is a new physics principle, and all these physics principles are on the back of your data booklet. So this is physics principle 3. So work energy theorem is when you're adding or removing energy to a system. So work is a scalar quantity because work is energy. Your light bulb can't run on negative energy. It can't run on energy to the left. Your light bulb either has energy or it doesn't have energy. So sometimes we do consider work positive or negative, and that just, it doesn't refer to direction, right? We wouldn't have work to the left, work to the right. What we refer to as positive or negative work is if energy is added or removed from the system. So if you're adding energy to the system, it's positive work. If you're removing energy, it's negative work. Okay, so work is done on a lazy cat by pushing it 54 centimeters across the floor at a constant speed of 50 newtons. What is the work done on the cat? Oh, this video here is, um, I guess I can show the video. The sound won't work with it, but I can show the video if I can get it to play. Well, I don't know how to get it to play. Pointer options. Pen, highlighter, arrow options, visible. There we go. So this is my cat, Millhouse, and he really likes being pushed like this on the floor. He can get pushed forever. It's like one of his favorite activities. I'm gonna skip ahead to my basketball moves here so you can see some sick basketball moves. Oh! And you think he's done. He doesn't want it anymore. Just kidding. There he goes. And just to prove he's alive, at the another basketball move. Just to prove he's alive. There he is. Yeah. Millhouse loves to be pushed. Okay, back to the question. Sorry. So work is done on the lazy cat by pushing it 54 centimeters across the floor with a constant force of 50 newtons. What is the work being done on the cat? So this is a Science 10 style question. It's very easy. If I give you a force and I give you a distance, yeah, you can just use your Science 10 style formula where work equals force times distance. Okay, you do have to be careful. So the force is given in newtons, and then the distance is given in centimeters. So that's got to be in meters. So 0.54 meters. You'd want to switch that into. So the work done on the cat is 27 joules. Right? And then to look at the units as well, we can use this formula to break down joules into something else. So a joule is equal to a newton meter as well, right? Because force is in newtons, distance is in meters. Well, how can that equal the other thing that we were talking about the other day? Well, remember, so joule equals a newton meter, but remember that we said that a newton is equal to a kilogram meter per second squared, and that meter stays on top. So it still ends up being kilogram meter squared per second squared like we were talking about before, but we can describe a joule as this, or if we want to break it down further, we can describe a joule as that. Let me give me a sec because I squared it. That as well, right? And we just use those formulas to help us figure that out. Okay, so another type of question. So this is more of what you'll see on a test. You might see one of those easy ones on a test, but this is more of what we do in Physics 20. So an 8-kilogram wagon moves along a horizontal sidewalk at a speed of 15 meters per second. Its wheels fall off, and now it has a frictional force opposite to the wagon's motion, which brings it to rest in 2 seconds. Determine the work done on the wagon. So the cool thing about this, the more physics we do, the more ways we have of solving this problem. So technically you could use work equals force times distance, right? And we could break down force into mass times acceleration. Work makes me mad. So we could break it down into that. So we have the mass of our wagon. We have the distance, or we don't have the distance as well, but we could find all that because we could use VI, VF, DAT like we did before, right? It comes to a stop at 0 meters per second. It starts off at 15 meters per second, and it comes to a rest in 2 seconds. So we have enough information. As long as we have 3 of 5, we could find both of that. But that's actually a lot more work than the new way that I'm going to show you. So we're going to use physics principle number 3, our work energy theorem, where work equals our change in energy. So because in this question the wagon is slowing down, we are changing our kinetic energy. So we can have EK final minus EK initial, because change is always final minus initial. And because our final speed is 0, we actually don't have any final kinetic energy. So we can say that our work is equal to negative our kinetic energy initial. And we know that our kinetic energy initial is just 1/2 mv squared with our initial speed. So it would be 1/2 our 8 kilogram wagon and our initial speed, which is 15 meters per second squared. 15 meters per second squared outside of the brackets. And that negative, well, I'll talk about the negative in a sec. So 1/2 times 8 times 15 squared gets us 900. But because that negative there, it'd be negative 900 joules. And all that negative means is if we start with kinetic energy and we end with no kinetic energy, friction is going to take it away. And every time you do a question where you get friction is the thing doing the work, then it's always going to be negative because friction always takes away your energy. So you can finish this problem here, give it a go, and you'll get 900 as well. If you find your acceleration, you find your distance using two different formulas, you'll be able to get 900 joules. It's just a little bit more work. Okay, and then another question that we were doing is this one here. So work is done against gravity in lifting a 50 kilogram box a vertical distance of 10 meters with a constant velocity. Calculate the amount of work done on the box. Okay, so this one we don't have an option. We have to use work equals our change in energy, because if you try to use work equals force times force times distance on this one, and mass times acceleration times distance, well, your acceleration, it says it's in the question, it's moving at a constant speed. So you get really confused. So I would try not to use that one, or else you're going to get confused on a test. Okay, so work equals our change in energy, but since we're taking a box and we're lifting it up like that, we're changing our potential energy this time. Okay, so it can be any type of change in energy you just want to specify. And in the question, I say that it moves up at a constant speed. So the reason I say it moves at a constant speed is that so that there's only one type of energy changing, to keep the question more simple. Okay, so our change in potential energy, so it's going to be our potential energy final minus our potential energy initial, and that equals our work. So if the box starts on the floor, let me draw a little picture. So this is the floor here. So this is our starting position for our box, and this is where it goes when it's listed a distance of 10 meters. Right, our reference point is the ground. So here, there is no potential energy because, well, our reference point is at a reference point. And anytime you're at your reference point, your potential energy is 0. So we have no initial this time. So it's just going to be our potential energy final. So it's just going to be mgh with our final height there. So our box is 50 kilograms. Our g is 9.81 meters per second squared. And then our final height is 10 meters above our reference point. So we plug all of this in. 50 times 9.81 times 10. And we get a positive answer because we're adding energy, we're lifting it up. 4905 joules. We got 3 sig digs in the question, so I should go 4.91 times 10 to the 3 joules. Okay. Sometimes it wants a positive, sometimes it doesn't. It'd be like a multiple choice question situation. Sometimes it's there, sometimes it's not. It doesn't really matter that much. Okay, so that's it. That's work. Just work equals change in energy, and work equals force times distance. So what we're also going to do is we're going to be adding it to some 2D questions that we did in our last unit. So in solving 2D questions, you must find the net force like we did in the last unit. And once the net force is found, you can use, our network equals force net times our distance. Okay, so yeah, in our last unit we learned to find F net. We just have to multiply a distance. It's not super tricky. So here we have a 20 kilogram wagon is pulled by a force of 40 newtons by its handle at an angle of 30 degrees to the horizontal over a distance of 10 meters. Calculate the work done. So you should be thinking in your head, what type of question is this? Well, this is a lawnmower question for sure. And we can draw out what's happening in the question. So we have a 20 kilogram wagon. So this is 20 kilograms. And it's being pulled with a force of 40 newtons. That's my force applied. Over a distance of 30 degrees from the horizontal. Okay. And it moves a distance of 10 meters. So if we want to find the net force for this, it's just like before, where not all this force being pulled at an angle actually goes into accelerating it. It's only the force in this x direction that makes it go. Okay, and it doesn't say there's any friction or anything, so we can write our F net equation as F net equals that force applied to the x. Okay. So to find that force applied to the x, this angle is already in RCS, so we can do 40 cos 30, or you can use SOHCAHTOA, and you'll get the same thing. So we have adjacent and hypotenuse, so we want to use that. So we go cos of 30 equals adjacent over hypotenuse. So we'd end up doing that. But because these angles for these questions are usually in RCS already, if you want to find the x, you just go magnitude cos angle, and you can find it. So our 40 cos 30 gives us 34.64101615 newtons, and that's our F net acting on our wagon, right? So all we have to do to bring it into this unit is work equals, or F net, times our distance equals our net work. So I take this number and I multiply it by my 10 meters that I travel, and I've got 3 sig digs in the question, so it's going to be 346 joules. That's my net work. And if the wagon starts from rest, what is its speed after 10 meters? Sure. So we have a few ways that we can do this. You could definitely use could you use VIVFDAT? I don't think we actually have enough information to do VIVFDAT. You'd have to do a lot more work. So if it starts from rest, we have that. And it moves a distance of 10 meters. And we could use F net equals ma, and we could find our acceleration. That's one way of doing it, and you could use VIVFDAT, but I want to use our new formulas today. So I'm just going to erase some of this. So we could also use our work equals our change in energy, and we're changing our kinetic energy here, right? So it's going to be kinetic energy final minus kinetic energy initial, and if we start with the speed of 0, we have no kinetic energy initial, so it's going to be work is equal to our kinetic energy final, like that. So we just have to rearrange this and solve for our V. So we move our 2 up top, we move our mass down below, and then we square root it, and we can solve for V. So 2 times the work that we just found, which is 346.4101615 joules. And then the mass of our wagon is 20 kilograms, and we square root it. And we get our final speed to be 5.89 meters per second. Okay, so you can use VIVFDAT, you can use that, a lot more options with this. Okay. Let's see what we have left. Okay, we got a little bit left. Okay, so another type of question that we can do is an inclined plane question. So Supergirl pushes on a 20 kilogram box at a constant speed up a frictionless 10-meter long ramp inclined at 30 degrees to the horizontal. What is the work done on the box by the girl? So this is an inclined plane question. Trying to spice it up with Supergirl. I think I was unsuccessful. So the incline is 30 degrees. And the box starts down here, and then the box ends at the top of the incline. And it says that the ramp is 10 meters long here. Okay, and the box is 20 kilograms. That's what we know. So think about this. What type of energy is Supergirl, can't believe that show's still on TV, giving the box by lifting it up, right? It says in the question, oh, I was drawing this picture this whole time. Sorry, this is my picture that I was drawing here. So 30 degrees, 20 kilograms, 10-meter long ramp. Sorry, you couldn't see that. So what type of energy is she giving it, right? What is the work done? You always need to think, well, she's either taking away or adding energy, obviously adding it. And it says that she's moving it at a constant speed. So by lifting it up that ramp, she's giving it potential energy. It's moving off the ground. Right? So it's got EP there and it's got nothing there. So we can say that work equals our change in potential energy, where our EP final minus our EP initial. Well, here I'm on the ground. The ground is my reference point. I have no initial potential energy, so my work is going to be equal to mgh final. So we know this is 20, we know this is 9.81, but this height here, is that 10? Well, it's not, because we always measure our vertical height, right? So what that means is if I take an object and I lift it to this point here, or I take an object and I lift it to this point here, although this is a hypotenuse line, this is a longer distance, I'm actually doing the same amount of work. I'm giving it the same amount of energy, because we always measure our height as a vertical height. So it doesn't matter if I lift at an angle or a vertical height like that, it's the same. So we can't use the 10 for our height, so we have to find this. And this is a triangle, right? So we can use SOHCAHTOA. We have opposite, we have hypotenuse, so sine. So sine of 30 degrees equals opposite over hypotenuse. Move the 10 up there. So we can find that height. This is 10 sine 30. So my object is 20 kilograms. My G is 9.81 meters per second squared. And then my height is, well, let me find it. 10 sine 30 is 5 meters. So my height is actually 5 meters that I'm lifting it off the ground. So 20 times 5 is 100 times 9.81 equals 981 joules. So that's how much work of potential energy is being put into that object. Okay. Long lesson today. Okay. So I got a board question here. Give it a go. Maybe don't pause it quite yet, because I'm going to help you out with something. So it says that it's 83 degrees, but she should always have a reference point. So this is like our 0 RCS reference point. So if it's 83 degrees between these completely, then that means it's going to be half. So this is 41.5 degrees. And this is 41.5 degrees, just to help you out a little bit. And it says that him and his friend hop on horses, and they attach 2 ropes to the stump. They each pull with 624 newtons. What is the network done if they move at 8 meters? So 624 newtons as well. Okay, so give it a go. See if you can try it. If you can't figure it out, I will go through it right now. Okay, so we have 2 vectors like that of 624 newtons, and each angle is 41.5 degrees. Okay, so if I add these tip to tail, it's not going to make a right angle triangle, right? This would be my net force like that. So what I can do is I can do an RCS chart. Okay, so vector 1 has a magnitude of 624 newtons. Vector 2 is 624 newtons. And then in terms of RCS, this is 0 degrees. So this is going to be 41.5 degrees. And then this one is going to be, well, it's going to be 360 minus 41.5. So it's going to be 318.5 degrees. This is my x, this is my y. So I go magnitude cos 41.5, magnitude cos 318.5, magnitude sine of 41.5, magnitude sine of 318.5. And I'm just going to do my on-screen calculator for this one. Put it up there so I can see. So 624 cos of 41.5 plus 624 cos of 318.5. And I get that as my x, and then I go second enter, switch all my coses to sines. And I get 0. What the heck? What's going on there? I'm just going to write these numbers down. So I'm just going to go 935 newtons, and then 0 newtons. What's going on there? Well, take a look. Let me draw this tip to tail diagram again. Right? They're equal magnitudes. Right? So this is my net force. Well, it makes sense. Like, it looks like it's all in the x right there, right? And remember that these have x components and y components. These have x components and y components. But if these are the exact same triangles, they're both 41.5, this is a positive y, this is a negative y, those y's are going to cancel out, and all we're left with is the x's. So to draw our final triangle, okay, this is positive, so my x is to the right, which is positive, and then my y is 0. So this is my final triangle. It just ends up being a line. So to bring this into this unit, it says that, well, my net force is equal to 935 newtons. And my distance, it says in the question that it moves at 8 meters. So I take my answer, my 935, and I multiply it by 8, and this is my answer. So this is what I get. I have 2 sig digs in the question, so I'd end up getting 7.5 times 10 to the 3 joules as my network that's done. Okay, so all this stuff from the last unit, you give it another shot at it, you can do it again. Okay. Simple machines. Okay. Last thing we're going to talk. Oh, second last thing that we're going to talk about is simple machines. So simple machines are a good example of this work equals force times distance. They rely on mechanical advantage, so they make things easier. Work done on one side must equal work done on the other side. So we can say work on the left must equal work on the right. So let's do a simple machine question. So we have a lever is used to lift a 2 times 10 to the 3 kilogram car 0.75 meters above the ground. Depending on where the fulcrum is placed, the lever needs to be pushed down 0.2 meters or 0.5 meters. Which position would make it easier to lift the car? So I'll draw this out on here. So what we can do, so this is my car over here. So we can place the fulcrum, this is my fulcrum, close to the car, and then push down here. This is my force. Or my other option is, it's hard to draw on here. I can place my fulcrum far away from my car, and I can push down on here, and that's my other option. So I'm hoping that you've experienced fulcrums in your everyday life and these simple levers here, and this would be easier. So try it out, like grab an eraser, grab a pencil, put something on the end of it. Yeah, I can show you what you can do. So if you just take, for example, a ruler, let me erase this. So if you just take a ruler and you put something on the end of the ruler, like an eraser, and here I've placed it far away. Look at that! I can't even lift it up. It's too much force because I have a flexi ruler here. I don't think I have a stiff ruler handy. But then when I place it over here and I lift it up, it's really easy. So what changes though? Let me do a side view here. When it's easier and it's super close, just pretend my fulcrum's here. This is my fulcrum here. Here's my fulcrum. So when it's easier and it's nice and close to the object that we're lifting up, right, you can see how big of a distance I have to move, right? To lift this up, focus on this hand here, I have to move it quite a bit. So the distance I move it is like that to lift it up. But if I pull my fulcrum over here and I want to lift it up, right, I only have to move it about this distance. So to make things easier, what we're doing is we're changing the distance that it has to be moved. Okay, so let me draw out so this is my easy one, and this is my hard one right here, right? So this is a big distance, and this is a little distance that we have to move it. Okay. So this is talking about a lift that's lifting up a car. So no matter how I set up my fulcrum and my lever, this car has to be lifted a certain height, right? I have to lift my car off the ground so that I can work on it. So no matter what, this is going to be 0.75 meters. So what we find is that whether we do either one, our work that we're doing equals our change in potential energy. So it's EP final minus EP initial. So we don't have any initial potential energy, so it's just going to be mgh. Whether we use this design or this design, well, our potential energy is going to be the same, right? It's going to be our car, which is 2 times 10 to the 3 kilograms, times 9.81 meters per second squared, times our height of 0.75 meters. So if I plug that in, I get 14715 meters. So over here on the right side, I get 14715 meters, or sorry, joules, not meters, sorry. 14715 joules. So that's how much energy I'm giving my car. So the work is actually me lifting on the other side. So it's got to be the work equal to the work done on this side. And on this side, I'm going to talk about work in terms of force times distance. So when we talk about work equals force times distance, this stays the same. So if I increase my, let me use a different color. If I increase my distance to keep this the same, my force has to decrease, and vice versa. If I decrease my distance, I have to increase my force. So this easier version here, when I have a bigger distance, I have less of a force, right? So over here, the work that I'm doing is 14715 joules, and that equals my force times distance. But here, I'm pushing down a bigger distance. So in the question, it says that this is 0.5 and this is 0.2. So if I move my distance down here and I do this as 0.5 meters, I find that my force is going to be much less. So I divide that by 0.5 meters. So my force to do that is this many newtons. But over here, to lift that car up and give it this much potential energy, if I divide it by my distance of 0.2, I find that it's a bigger number. So when we're talking about easier, easier refers to force. Right? To make things easier, we need to increase our distance. That's what we're doing. Okay? That's how simple machines work. So give those a go in the homework and see how that goes. Okay, one last thing we're going to talk about, super easy power. So I have some questions for you. If Mike uses 200,000 joules of electrical energy and Sarah uses 5,000 joules of electrical energy, who uses more? That's Mike. But then if I told you Mike used that in a year and Sarah used that in a day, ooh, well, that's a little bit different, right? Because if Mike uses 200,000, there we go, 2,000 joules in 365 days in a year, while Sarah, right, if we compare that to Sarah, uses 5,000 in one day, well, we'd have to take this and divide it by 365. So if we take 200,000 and we divide it by 365, we end up getting, well, Mike only uses that much per day. So if we do it in not the amount of time, well, Sarah actually uses way more energy than Mike, right? So that's why when you get your power bill, it's in power and not just the amount of energy used, because you need time. So power is a rate, how fast you use that energy. So our power formula is power equals work over time, or power. The unit for power, which is a little bit confusing, is a watt. So it's got the symbol W, and this here is work, which is joules. I don't know why they do that. So lots of times when I do a watt, I put these bars on top so I don't confuse it with work. But yeah, and then time in seconds. Okay, so I got a board question for you. What are the standard units for 1 watt in kilograms, meters, and seconds? So give this a go, and then pause the video, and I will go through it and see if you can figure out what a watt is equal to. Use that new formula to help you. Okay, so power equals work over time. So power is in a watt, and then work is in joules, and that's in time. So it wants the answer in kilograms, meters, and seconds. So I have to figure out what a joule is equal to. So I'm going to use EP equals mgh, where mass is in kilograms, g is in meters per second squared, and height is in meters, and it's meters times meters, so I'm going to call that meters squared. So now I'm going to keep that time on the bottom. Instead of writing joule, I can write kilogram, meters squared, per second squared. Oops, sorry. Time is in seconds, joules per second, sorry, so the seconds is down there. So what we end up getting is it's a kilogram meter squared per second squared second. And if I have seconds squared times seconds, I end up getting seconds cubed. So a watt is equal to that. Okay, and let's do a numbers question. So a 50 kilogram student runs up 3 flights of stairs at a constant velocity. Right, so if she's running up the stairs, then she must be changing her EP. Here she has EP, here she has no energy, she's doing it at a constant speed. The time it takes her is 9.81 seconds the first time, the second time takes her 19.62 seconds. What was the power she exerted for both times up the stairs? Okay. Last question, a pen's dying, got to get a new pen. So we're going to use power equals work over time. And you have to figure out what type of work they're doing. So work is our change in energy, and she's changing her potential energy. So this is potential energy final minus potential energy initial. right? And she doesn't have any initial potential energy because she starts at the ground. So her power is going to be equal to EP final, so mgh final, all divided by our time. Okay. She has a mass of 50 kilograms times 9.81 meters per second squared times our final height. She goes 10 meters above the ground, and she does it all in a time of 9.81 seconds. Right? 9.81, 9.81 end up canceling out, so the power she exerts is 500 watts. Okay, and if we do the exact same thing, but instead of taking 9.81 seconds, she takes 19.62 seconds. Right. Might have to type that in to your calculator. 50 times 9.81 times 10 divided by 19.62. Well, if she takes double the time, she uses half the power. So 250 watts when she takes double the time. Okay. Whew, that was a long lesson. Span it out over 2 days. Maybe watch the lesson one day, try some homework, and then, no, we're not going to do that. And then, yeah, give it a go. So this is all the homework. I know it's a ton. We'll see how it's going. I don't know. I might even give you Friday to work on that too, because I don't want to overwhelm you. Yeah, maybe we won't do springs on Friday. Maybe we'll just do this over the next 3 days. And then, yeah, email me if you have questions. I can go through stuff. Remember, I posted the answers to the workbook, so take a look in that as well. But yeah, there's a lot of little stuff in here, so do your best, and I'll give you some time to work on it. Okay, thanks for watching.